Greetings and welcome to Distillate. In the previous classes, we have discussed about various concepts. For example, we studied about the ideal gas equation, which related pressure, volume, number of moles and temperature with different values of R according to units. R has value 8.314 when the unit is joule per mole Kelvin. R is 0.08206 when the unit is liter atm per mole Kelvin, and R is 1.987 when the unit is calorie per mole Kelvin. All right. Then we discussed about how to convert something from mole percent to weight percent and weight percent to mole percent. But before that, we also studied certain concepts like Dalton's law, where we said that the summation of all partial pressures of all components in a mixture is equal to the total pressure. Similarly, we studied Amagat's law, which stated that the summation of partial volumes of all components in a mixture is equal to the total volume of the mixture. All right. Then we studied a very important relation for ideal gases, that is mole percent is equal to volume percent, which is equal to partial pressure percent. All right. Then we studied how to convert something from mole percent to weight percent or from weight percent to mole percent. So in order to convert something from mole percent to weight percent, we studied that we have to take basis. If we have to convert from mole percent to weight percent, then we have to take basis as 100 kilomole of mixture. All right. When we take 100 kilomole of mixture, then from that we calculate moles. From moles, we calculate weight by multiplying moles by the molecular weight. We get the weight. Then we get the total weight by adding all the weights. And finally, we get weight percent, or you can say weight fraction, is equal to individual weight upon total weight. All right. This is what we studied. After that, to convert something from weight percent to mole percent, we studied that the basis in case of weight percent, we take it as 100 kg of mixture. We take our basis as 100 kg of mixture. Using that, we get the individual weights. From the individual weights, we get individual moles, because weight upon molecular weight gives us the number of moles. After that, from individual moles, we'll get the total moles. And finally, we get mole fraction is equal to individual moles upon total moles. All right. This is what we discussed in the previous class, and we discussed certain problems based on this. Now, today, we are going to study about vapor liquid system. So when we are studying about the vapor liquid system, the first thing that comes into mind is the states of matter. All right. So we all very well know about the three states of matter: solid, liquid, and gas. In solids, the intermolecular distance is negligible, while the intermolecular forces are very high. All right. The intermolecular interactions are very high. When we talk about liquids, in that case, we have moderate intermolecular distances as well as moderate intermolecular forces. While in case of gases, there is a very high intermolecular distance, and because of that, the interactive forces or intermolecular forces in gases are negligible. All right. Then when we study about the liquid state in general, so we know that liquids, they are obtained at moderate pressures, because if we keep pressure very low, then we'll get something as solid. And if we keep pressure very high, I'm so sorry. If we keep pressure very low, then we'll get gases. And if we keep pressure very high, then we are going to get solids, right? So liquids are generally obtained at moderate pressures. And usually liquids are incompressible in nature. And because of that, a significant increase in pressure would lead to a very small change in volume. So you can see that from this graph over here, we have increased the pressure from this low to this high, and the change in volume is only this much, right? for this large change in pressure, the change in volume is almost zero. All right, almost close to zero. Right. That is why they are generally concerned to be incompressible, considered to be incompressible. And when we talk about liquids, so if we keep pressure constant, if we keep pressure constant, then we get liquids in a particular temperature range. That is, if the temperature lies somewhere between the freezing point and the boiling point of the substance. All right. So for example, at a pressure of 101.325 kilopascal, or simply if I should say at 1 atm, 1 atmospheric pressure, water's freezing point is 0 degrees Celsius and water's boiling point is 100 degrees Celsius. Hence, water is obtained in liquid state between these temperatures. If you increase the temperature over 100 degrees Celsius, then you will get vapor. If you decrease the temperature less than 0 degrees Celsius, then in that case you will get solid. All right, ice. Right. Then when we talk about gases, then gases are generally obtained at moderate or low pressures. They're highly compressible in nature. All right. And they are obtained at a temperature that is greater than the boiling point of the substance. Okay. The temperature should be greater than the boiling point of the substance. Then we'll get it in the gaseous phase. All right. Now we come to a very important concept, that is vapor liquid equilibrium. And this concept is going to be carried along with you all till a very long time. All right. So you people need to understand this concept very nicely. All right. So when we talk about equilibrium, vapor liquid equilibrium, then let's say we are taking an air water system. All right. We are taking air water system. So we know that water, if we have water, then water in its liquid form would obviously tend to evaporate, right? Water would tend to evaporate and form water vapor. Okay. At the same time, water vapor would tend to condense. All right. So you should know these two terms, condensation and evaporation. Evaporation is the process of conversion from liquid to vapor, and condensation is the process of conversion from vapor to liquid. All right. So when water, or you can say the liquid and the vapor phase are in contact, then phase transition, that is movement from liquid phase to vapor phase or vapor phase to liquid phase transition can take place in both the ways. That is, water liquid evaporates to form water vapor and water vapor condenses to form water liquid. Now, out of these two processes, one of them would be dominant. That means either water would be evaporated more in comparison to water vapor that is condensed, or water might be condensed more than it would be evaporated. So whichever is the dominating process, if evaporation is dominating, then overall evaporation occurs. If condensation is dominating, then overall condensation occurs. All right. When both these processes occur at the same rate, all right, when both these processes occur at the same rate simultaneously, then this particular system is said to be under dynamic equilibrium. All right. Then this system is said to be under dynamic equilibrium. All right. So both ways, the transition from vapor to liquid and liquid to vapor has to be equal. Only then we can say that equilibrium has been achieved. Now let's say in this case, once equilibrium has been achieved, now all of a sudden, let's say I add water vapor to air. All right. Let's say I add water vapor to air. Now again, the amount of water in the vapor phase has increased. Therefore, to balance this particular water vapor, it will start to come into the liquid phase. Because again, since water here is more than water in the liquid phase, therefore condensation would start dominating. All right. Therefore, it would again start movement. Again, the change would start. Then again, we'll have to wait till equilibrium, till the new set of equilibrium conditions are established. All right. So once the system has attained equilibrium, if we bring disturbance to that system, then we'll have to wait for new equilibrium conditions to be established. All right. Now, by understanding the concept of vapor liquid equilibrium, let's now define vapor pressure using VLE. VLE is vapor liquid equilibrium. So if we keep a temperature, if we take a given temperature, then at a given temperature, when vapor and liquid phase of a substance are in equilibrium with each other, then the absolute pressure at that point is known as vapor pressure. All right. So at a particular temperature, if water, that is liquid phase and vapor phase, are in equilibrium with each other, at that particular point, the pressure is equivalent to the vapor pressure. All right. It is equivalent to the vapor pressure. All right. Hope you people are clear with this. Now, all right. Then we talk about variables that are considered in VLE. All right. So while dealing with vapor liquid equilibrium, these variables are going to come into picture again and again for all the laws that we'll be dealing with, for everything. These variables have to be kept in mind. Therefore, I have covered these variables over here. So don't get confused further. If you want, you can pause the video and note these down. We'll be using all of this further. All right, all these variables we'll be using further. So please do not get confused. All right. So X is mole fraction in the liquid phase. X dash is mass fraction in the liquid phase. So whenever you see X, that means you have to go to the liquid phase. If it is X, then it is mole fraction. If it is X dash, then it is mass fraction. Similarly, Y is mole fraction in the vapor phase and Y dash is mass fraction in the vapor phase. PA is partial pressure of component A in the vapor phase. And P naught A is the vapor pressure of component A. P naught A might also at times be written as PAS. So please do not get confused. It's the same thing. And finally, capital P is known as the total pressure. All right. So once we have dealt with that, now let's go to the liquid system and liquid laws. So when a mixture is in the liquid phase, there are two laws that govern this system. The first law is Raoult's law, while the second law is the Henry's law. So when we talk about the laws, the Raoult's law, it relates partial pressure. Partial pressure, as I told you, it is denoted by PA. So it relates partial pressure and mole fraction in the liquid phase. Remember, this is mole fraction in the liquid phase. All right. So liquid phase mole fraction and partial pressure. Partial pressure is always in the vapor phase. All right. Partial pressure is always in the vapor phase. This is the pressure of the vapor. All right. Pressure in the vapor phase. All right. So it relates the partial pressure in the vapor phase and the mole fraction in the liquid phase. So at a given pressure, at a given temperature, the partial pressure of a component in the vapor phase is equal to the product of vapor pressure, that is P naught A, and the mole fraction of the component in the liquid phase. All right. So this is my Raoult's law. Then, according to Dalton's law, we know that sum of all partial pressures is equal to the total pressure. And we know that by Raoult's law, partial pressure is equal to vapor pressure into mole fraction in the liquid phase. All right. So sigma pi is going to be sigma pi naught xi. So that is going to be sigma pi naught xi, which is equal to the total pressure. All right. When we apply Raoult's law in vapor liquid equilibrium, then we use the equation for Raoult's law. PA is equal to P naught A XA. This is the Raoult's law that we have. And then for gaseous system, we derived in the previous class that mole percent is equal to partial pressure percent. Hence, we get mole fraction YA. Why YA? Because it is in the gaseous phase. So for gaseous phase, we have mole fraction in the gaseous phase, that is Y. All right. So YA, which is the mole fraction of A in the gaseous phase, is equal to partial pressure of A upon total pressure. Hence, we get the partial pressure of A in the vapor phase is equal to mole fraction of A in the vapor phase multiplied by the total pressure. All right. Hence, if we keep this as equation number 1 and keep this as equation number 2, then from equation number 1 and 2, we can get YA into P is equal to P naught A into X. All right. This is a very important equation, and this is quite often going to be used in every in many courses further. All right. For example, when we study thermodynamics, then also we will be studying this equation once. All right. So this equation is quite important. YA into P is equal to P naught A into XA. So based on all these factors that we have taken into account, let's solve a few problems. All right. So let's read this problem once. A liquid mixture containing A, B, and C is boiled at 65 degrees Celsius and 570.46 kilopascal. This G after pressure, whenever you are given pressure value and then a G is written in the bracket, that G implies gauge pressure. That G implies gauge pressure. All right. But whenever we are doing our VLE calculations, we always need absolute pressure. So absolute pressure is equal to gauge pressure plus atmospheric pressure. Keep this thing in mind. Absolute pressure is equal to gauge pressure plus atmospheric pressure. Now, atmospheric pressure is equal to 1 atm. All right. Atmospheric pressure is equal to 1 atm, and 1 atm is equal to 101.325 kilopascal. Hence, the total pressure here, that is the total absolute pressure over here, is going to be equal to gauge pressure 570.46 plus atmospheric pressure 101.325. All right. This is equal to 671.785 kilopascal. This is basically the total pressure that we have to consider. All right. Then the mole fraction of A in the ternary vapor mixture in equilibrium with the liquid is found to be 0.491. Remember, mole fraction of A in the vapor mixture. That means this is YA. All right. This is YA. All right. Assuming ideal behavior of liquid and vapor mixture, estimate the composition of the vapor mixture. All right. They have given vapor pressure of C, P naught C, as 3.293 kilopascal, and mole fraction of C in the liquid mixture, that means XC, is given to be 0.7734. All right. So hopefully you people have understood this question for now. Question. I have not done the solutions yet. The question, hopefully it is clear with. All right. Now we'll move on to solve this question. So while we are solving this question, we know that the total pressure to be taken is 671.785 kilopascal. All right. That is the total pressure that we need to take. They have given us YA is equal to 0.491. All right. Now, we know that for an ideal gas mixture, okay, for an ideal gas mixture, we know that mole fraction or mole percent is equal to partial pressure percent. All right. So mole percent is nothing but 0.491 for A, and the partial pressure percent is equal to partial pressure of A upon total pressure. All right. So from here, the partial pressure of A is going to be 0.491 into the total pressure, that is 671.785. That gives us 329.846 kilopascal. All right. 329.846 kilopascal. All right. Then next thing they have given is about vapor pressure of C. So we know that P naught C they have given to be 3.293 kilopascal. All right. 3.293 kilopascal. Okay. So now, in order to find the partial pressure of C, we are going to use the Raoult's law. Okay. We are going to use the Raoult's law. So we know that by Raoult's law, partial pressure of a component is equal to vapor pressure of that component into mole fraction of that component in the liquid phase. All right. Now they have given mole fraction of this component C in the liquid mixture as 0.7734. So we have XC equals to 0.7734, implies PC would be 3.293 into 0.7734. That is going to be 2.547 kilopascal. All right. This is going to be the partial pressure of C. All right. Then we are going to apply Dalton's law. Okay. So by Dalton's law, we have PA plus PB plus PC is equal to the total pressure. We have the total pressure. We have just calculated PC and PA. All right. So on the basis of that, we can calculate PB, which is total pressure minus partial pressure of A minus partial pressure of C. Hence, PB is going to be equal to 339.392 kilopascal. All right. Let's see. So we have to estimate the composition of the vapor mixture. That means composition of vapor mixture implies Y. So we have to calculate YA, YB, and YC. So we know that YA is going to be, since we know that mole percent is equal to partial pressure percent, therefore YA is going to be partial pressure of A upon total pressure. All right. So that is going to be equal to 0.491, which was already given in the question. All right. YA 0.491 was given in the question. All right. Then YB we calculated already. YB we already calculated over here. YB is equal to, all right, YB we didn't calculate. We calculated YC. YC we had. Okay, we don't even have YC. So YB, to calculate YB, we are going to have PB upon P. So that is partial pressure of B, 339.392 upon the total pressure, that is 671.785. So this is going to be equal to 0.5052. And YC is going to be partial pressure of C upon total pressure, which is equal to 0.0038. All right. So this is the composition in the vapor phase. Hope you people are clear. Hope you people have now understood how to apply the various gas laws. All right. So using this example, I have tried to explain how to use Raoult's law in combination with Dalton's law in order to calculate composition in vapor mixture. Okay. Let's do another example. Over here, they have given a solution containing 50% benzene, 20% toluene, and rest of it xylene by weight is in contact with its vapor at 212 degree Fahrenheit. This temperature is given in degree Fahrenheit. Now, let me tell you how to convert degree Fahrenheit to degree Celsius. So it's a very simple conversion. When we calculate or convert anything from degree Fahrenheit to degree Celsius, then the conversion is given as degree Fahrenheit, whatever is the temperature in Fahrenheit, minus 32 upon 180 is equal to degree Celsius upon 100. All right. This is the conversion for degree Fahrenheit to degree Celsius. All right. So degree Fahrenheit minus 32 upon 180 is equal to degree Celsius by 100. All right. So from here we get 212 degree Fahrenheit is equal to 212 minus 32 upon 180 is equal to degrees Celsius upon 100. Hence, from here, the temperature in degrees Celsius, you get it as 100. All right. Hence, which is actually equal to 100 plus 273, that is 373 Kelvin. All right. So this is how you convert from Fahrenheit to Celsius. All right. So calculate the total pressure and molar composition of the liquid and vapor. Okay. And they have given vapor pressure data for benzene, toluene, and xylene. All right. So you can please go ahead, pause the video, and try to solve the problem. All right. So hope you people have tried to solve this problem. If you've managed to solve, then very well. If you've not, then please have a look at this. So in the question, we have been given benzene, toluene, and xylene. So I'll be taking benzene as B, toluene as T, and xylene as X. So based on that, let's do the calculations. So I have the component. First of all, let's go with the liquid phase, since we have been given the liquid phase composition. A solution containing 50% benzene, 20% toluene, and rest xylene by weight is in contact with its vapor. So that means this is my liquid, which is in contact with my vapor. So first of all, let's deal with liquid weight percent. Okay, this is what has been given to us. So we have our components, benzene, toluene, and xylene. Now benzene is basically C6H6. All right. Toluene is a CH3 group attached to this, and xylene is another CH3 group attached to this. All right. So that gives xylene. So based on that, we'll be able to get the molecular weights as well. So first of all, let's get the weights. So we know that since we have to convert from weight to mole percent, therefore we are going to take basis as 100 kg of mixture. All right. When this is done, then we have benzene equals to 50 toluene is equal to 20, and the rest is xylene. That means 100 minus 50 minus 20. That gives you 70. All right. Then we have to calculate the molecular weights of each. So benzene is C6H6, that is 12 into 6 plus 6. That gives us 78. Similarly, toluene gives us 92 and xylene is 106. All right. When we have got the molecular weights, then we are going to calculate moles. All right. So to calculate moles, weight upon molecular weight. So this is going to be 0.641. This is going to be 0.2174. And this is going to be 0.283. All right. Then the next step is to find the sum of all. That is 1.1414. All right. Then we are going to get the mole fraction. All right. So mole fraction is going to be moles upon total moles, right? So this is 0.56. Then this is 0.19. And this is 0.25. So when we add, we will get 1. Hence, our calculations are correct. Okay. Once we have got the mole fraction, then we'll go to the next part of the question, where they are saying that calculate the total pressure and molar composition of the liquid and vapor phase. So we have done this part. We have calculated the molar composition of the liquid mixture, liquid phase. All right. Then how do we relate the liquid phase to the vapor phase? Using Raoult's law. Okay. So by Raoult's law, we have PA is equal to P naught A into X. That is how you give. So this is the liquid phase mole fractions. Hence, this is going to be X. Hence, the partial pressure of B, partial pressure of T, and partial pressure of xylene, we'll calculate using the mole fractions as well as the vapor pressure data that has been given. All right. So for benzene, it is going to be 0.56 into 178.6 kilopascal. So that is going to be equal to 100.016 kilopascal. All right. Similarly, for toluene, we are going to get 74.6 into 0.19. That is equal to 14.174 kilopascal. All right. And finally, for xylene, we are going to get 0.25 into 28. That is 7 kilopascal. All right. So these are our 3 partial pressures. All right. These are our 3 partial pressures. All right. Then we know by Dalton's law. By Dalton's law, we know that summation of partial pressures of each component is equal to the total pressure, implies the total pressure is going to be equal to partial pressure of benzene plus partial pressure of toluene plus partial pressure of xylene. That is going to be equal to 121.19 kilopascal. All right. This is the total pressure. Okay. So we have solved this part where we had to calculate the total pressure. And finally, we have to find the composition of the vapor phase. So we know that in the vapor phase, mole percent is equal to partial pressure percent. Hence, we are going to get YB is equal to partial pressure of B upon total pressure. So partial pressure of B is 100.016 and total pressure is 121.19. Hence, this is equal to 0.825. Similarly, YT is going to be PT by total pressure, which from our calculations, we'll be able to get 0.117. And finally, the mole fraction of xylene in the vapor phase is equal to partial pressure of xylene upon total pressure. that is equal to 0.058. So when we add these, we'll get 1. Hence, our calculations are correct. All right. So this was your example number 2. Here we were given the composition by weight, liquid composition by weight. So we calculated the molar composition by weight, molar composition in the liquid phase. Using the molar composition and the vapor pressure data, we calculated the partial pressures in the vapor phase. And using the partial pressures, we calculated the total pressure. And using total pressure as well as partial pressure, we calculated the mole fraction in the vapor phase. All right. Now, this is example number 3. Try to solve yourself. Pause the video and solve yourself. Hope you people have managed to solve this problem. If you haven't, then have a look at the solution. It is given that a mixture of benzene and toluene containing 30% benzene by mole is in contact with its vapor at 373. That means this is XB. All right, XB is 0.3. All right, calculate the vapor pressure of benzene. We have to calculate P naught B. And they have given us data about toluene and the total pressure in the vapor space. All right. So they have given us P naught T. They have given us P. All right. So now we know by Raoult's law, we know that by Raoult's law, partial pressure of benzene is going to be equal to vapor pressure of benzene into its mole fraction, while partial pressure of toluene is going to be equal to partial pressure of vapor pressure of toluene into its mole fraction. All right. Hence, the total pressure, that is partial pressure of benzene plus toluene, according to Dalton's law, is going to be equal to P naught B XB plus P naught T XT. All right. Now, in the problem, they have given XB to be 0.3 and XT they have 0.7, because 1 minus 0.3 is going to be 0.7. All right. Therefore, we get 760, which is the total pressure, is equal to P naught B, which is unknown, into XB, that is 0.3, plus P naught T, which is 533 millimeters of mercury, into 0.7. Now remember, whenever you're using this equation, the unit of total pressure and vapor pressures need to be the same. All right. So if we have taken millimeters of mercury here, so we'll take this also in millimeters of mercury, 533. And we'll get P naught B also in millimeters of mercury. All right. So when we solve this problem, we get 760 minus 533 into 0.7 upon 0.3. So that is going to be equal to 1289.667 unit, same, millimeters of mercury. This is your answer. All right. This is your example number 4. Pause the video and try to solve it yourself. Hope you could solve this problem. If you haven't, then let's see the solution. The vapor pressure of ether with molecular weight of 74 is 58.928. P naught ether, let's call it E. So P naught E is equal to 58.928 at 293. If 3 grams of a compound A, it is unknown. Which compound is this? This is unknown. It is just given 3 grams of compound A are introduced and dissolved in 50 grams of ether at this temperature. Remember, this is my weight. All right. This is my weight. Weight of A, weight of ether. All right. The vapor pressure falls to 56.795 kilopascal. All right. The vapor pressure, it falls to 56.795 kilopascal. This vapor pressure is not P naught E, it is the pressure of the vapor phase. So since now you have a vapor mixture, therefore the vapor pressure is going to be equal to the total pressure. Okay, so this is basically your total pressure, that is 56.795 kilopascal. Okay, find the molecular weight of A. This is what you need to find. And one thing that they have given is that assume the solution of A in ether is highly dilute. So since they have mentioned that the solution of A in ether is highly dilute, that means we'll take mole fraction of A tends to 0. All right, mole fraction of A, it tends to 0. This is one thing that they have said by saying that assume that the solution of A in ether is very dilute. That means very negligible amount of A is added. The number of moles of A are negligible in comparison to that of ether. That is why they have given us this. All right. So remember, whenever you get highly dilute solutions, this implies that mole fraction of the solute tends to 0. All right. Remember this thing. So since XA tends to 0, that means the total pressure is going to be equal to P naught ether into mole fraction of ether. Okay. Now this XE we cannot take tending to 1, of course, right? Because obviously there has been a decrease in the pressure, right? There has been a decrease in pressure. So it's going to be 0.999 something, but it's not going to be equal to 1. All right. So keep that thing in mind. All right. We are going to take P naught. We are going to get P naught AXA, this entire term tending to 0. But this is going to be some value. All right. So we cannot take this tending to 1. All right. So for that, we are going to calculate XE. XE is nothing but mole fraction of ether. All right. Mole fraction of ether. Now see that they have said that we have dissolved A in 50 grams of ether. So weight of ether is 50 grams and molecular weight of ether they have given to be 74. So it is 50 by 74 upon 50 by 74 plus 3 by, let's assume molecular weight of A as Me. All right. So on the basis of that, we can get XE. All right. We'll get XE. Okay. Now they have given, according to this equation number 1, since our total pressure has reduced to 56.795, therefore, using this equation, P equals to P naught EXE, we are going to say 56.795 is equal to vapor pressure of ether, that is 58.298 into mole fraction of ether, that is 50 by 74 upon 50 by 74 plus 3 by Me. All right. So when we solve this equation, we are going to get Ma equals to 118.22. 118.22 gram per mole is going to be the unit. All right. 118.22 gram per mole. This is your example number 5. Pause the video and try to solve this problem yourself. Hope you could solve this problem. If you haven't been able to solve this problem, let's see. The vapor pressures of two pure liquids A and B are respectively 100 kilopascal and 60 kilopascal. So this is P naught A and this is P naught B. All right. The concentration of A in the vapor in equilibrium with a solution of A and B is found to be 50 mole %. So that means this is the concentration of A in vapor. Ya is equal to 0.5. Determine the total pressure, the composition of the liquid as well as the total pressure of the vapor. All right. So in order to do this problem, we have P naught A is equal to 100 kilopascal, and P naught B, we have 60 kilopascal. All right. We have YA equals to 0.5, which would give us YB as well equals to 0.5. All right. Then let us assume that mole fraction of A in the liquid phase is XA. This value we don't have. We are going to assume it as XA. All right. Therefore, XB, the mole fraction of B in the liquid phase, is going to be equal to 1 minus XA. Since we know that summation of mole fractions is equal to 1. Hence, XB is going to be equal to 1 minus XA. All right. Then, by Raoult's law, we know that by a combination of Raoult's and Dalton's law, we know that total pressure P is equal to P naught A XA plus P naught B XB. All right. So P naught A is 100. So 100 XA plus 60 into XB, where XB is 1 minus XA. Hence, we get this as 60 plus 40 XA. This is the total pressure P. Okay. This is the total pressure P. Mark this as equation number 1. All right. Mark this as equation number 1. Now, once we have the total pressure equation and we have YA, YB, P naught A, P naught B, then we can say, using the rule that mole percent is equal to partial pressure percent, we can simply say that YA is equal to PA by P, where PA is nothing but P naught A XA and P is nothing but 60 plus 40 XA, right? And they have also given P naught A as 100. So 100 upon 60 plus 40 XA. And YA they have given to be 0.5. Okay, so solving 0.5 is equal to 100 upon 60 plus 40 XA gives us XA. Okay, XA, the value of XA you will get as 3 by 8. All right, the value of XA would be 3 by 8, which is 0.375. And similarly, we will get XB as 5 by 8. All right, we will get XB as 5 by 8. So this is the A part of the problem. We had to find the composition of the liquid. All right, so we have found XA and XB. Then to find the total pressure, we have the equation 60 plus 40 XA. In place of XA, we are going to put 0.375. So the total pressure, it comes out to be 75 kilopascal. All right, 75 kilopascal. Then this is your example number 6. Try to solve this problem yourself. Pause the video and try to solve it yourself. Hope you could solve this problem yourself. If not, then let's see the solution. A liquid mixture containing 25% A, 30% B, and rest C is in equilibrium with vapor, which contains 50% B. All percentages are on mole basis. The equilibrium pressure and temperature are 200 kilopascal and 350 Kelvin. At 350 Kelvin, the vapor pressure of C is 50 kilopascal. What is the percentage of A in vapor? So let's see how this problem is done. So we have been given that XA is equal to 0.25, XB is equal to 0.3. Hence, XC would be 1 minus 0.3 minus 0.25, which is 0.45. All right. And we have also been given that YB is 0.5. All right. Now they have given P naught C as 50 kilopascal. And they have asked us to calculate YA, right? So for YA, we either need P naught A, PA, and total pressure, or we can calculate YC somehow, and then we'll get YA equals to 1 minus YB minus YC. So that seems like an easier alternative. So we'll calculate YC. All right. So to calculate YC, we need PC. So by Raoult's law, we can say PC is equal to P naught C into XC. Both the values we have. 50 into 0.45. All right. 50 into 0.45. Hence, we get PC is equal to 22.5 kilopascal. All right. PC is equal to 22.5 kilopascal. Once you get PC equals to 22.5 kilopascal, and they have given that the total pressure is 200 kilopascal. Total pressure P is 200 kilopascal. Hence, we can get YC is equal to PC upon P, that is 22.5 upon 200. Hence, YC is equal to 0.1125. All right. So since we have got YC, therefore getting YA is very easy. 1 minus YB minus YC. So YB is given to be 0.5. YC we have calculated 0.1125. Hence YA we will get as 0.3875. All right. This is YA. That's all that was there in the question. All right. But since we are doing this problem, so let's try to find out something else. So we have not been given P naught B and P naught A. So let's try to find out P naught B and P naught A using Raoult's law. So the question is over till here, 0.3875. If you have got 38.75%, then that's your answer. All right. Now we are going to find out P naught A and P naught B, just for the sake of discussion. All right. So we know that the total pressure is 200 kilopascal, and we know that YB is equal to 0.5. All right. Therefore, we get PB is equal to YB into P, that is 100 kilopascal. All right. PB is equal to YB into total pressure. All right. So that is equal to 100 kilopascal. Now this 100 kilopascal is nothing but P naught B XB. Therefore, we get P naught B from here as 100 upon XB. XB was given to be 0.3. Hence, we get P naught B equals to 333.33 kilopascal. All right, that is P naught B. And similarly, we have YA. We have YA is equal to, as we calculated 0.3875. So we know that PA is equal to YA into total pressure. Hence P naught A is going to be equal to PA by XA. So that is Y into total pressure upon XA. So when we do the calculations, we get 310 kilopascal. All right, that's P naught A. All right, so from these problems, you could figure out that if we have a small amount of information about vapor liquid equilibrium, we can get all the possible variables: vapor pressure, partial pressure, total pressure, mole fraction in vapor and liquid phase. We can get all these informations using some variables that are given to us. All right. So that's all. These were the 6 examples that I had brought to you people for vapor pressure, or basically for Raoult's law. All right, for the application of Raoult's law and vapor liquid equilibrium. All right, so these were the 6 examples that I had brought. You people can again see the video and try to get the concept of these examples. All right, then we'll move on to the next part, next law, that is Henry's law. Henry's law is also used when we have a solution. All right. So in Henry's law, we can say that mole fraction, it is again based on the same concept as that of Raoult's law. Even in Raoult's law, we used to say that the partial pressure is proportional to the number of moles. Partial pressure in the vapor phase is proportional to mole fraction in the liquid phase. The same thing is applicable to Henry's law as well. Just Henry's law is a special case of Raoult's law, where the saturation pressure or the vapor pressure of A is equal to the Henry's constant HA. All right, Henry's constant HA. So from here we get Henry's law as PA is equal to HA into XA, where HA is the Henry law's constant. Okay, or we can say Henry's constant. All right. So Henry's law gives solubility of the gas in liquid in terms of its mole fraction. All right, that is how Henry's law is important. Now the question is that why do we have 2 different laws for determining the vapor pressure, or for determining the partial pressure? Why do we have 2 different laws? When to use Henry's law and when to use Raoult's law? When can I use the law PA is equal to P naught A XA? And when do I use the law PA is equal to HA into XA? So remember, Henry's law is valid for highly dilute solutions. Okay, that is when XA tends to 0. All right, when XA tends to 0, it is there where the Henry's law is very important. All right, where the Henry's law is very important. All right, and then Raoult's law is valid when XA is close to 1. All right, when XA is going to be close to 1, then we are going to use Raoult's law. So that also means that if, let's say, we have a mixture of A and B, all right, then if XA tends to 0, that means XB tends to 1. XB is very close to 1, right? So when XA tends to 0, then it is a highly dilute solution, which means Raoult's law would explain Henry's law would explain it. PA is equal to HA into XA, right? That is what will be done by Henry's law. While the second component, that is PB, will be explained by the Raoult's law. So PB is equal to P naught B XB. All right. So this is my result. In case we have highly dilute solutions, then one component is going to be explained by the Henry's law, the one which has a lower concentration, which has concentration tending to 0. That would be explained according to the Henry's law, while the second component is going to be explained according to Raoult's law. All right, the second component is going to be explained according to the Raoult's law. All right, so this concept actually comes to picture when we talk about solutions. So we'll be dealing with this concept more in solution thermodynamics. All right, so for now, I have just given you the basic formulas, but we'll be discussing with these concepts more in detail in solution thermodynamics. All right. So let's do this problem. An aqueous solution of acetaldehyde contains 2% acetaldehyde by weight. The partial pressure of acetaldehyde over the solution is found to be 41.4 kilopascal. Now you can see it is 2% by weight. So first of all, we need to convert it to by mole. Okay, we need to convert it into by mole. So when we do that, so to convert from weight percent to mole percent, we need to take, let me do it here. We need to take basis. We need to take basis as 100 kg of mixture. So that means we have acetaldehyde and we have water. All right. So the weight of acetaldehyde is 2 kg. Water is hence going to be 98 kg. Molecular weight acetaldehyde is CH3CHO. Right. So that is 12 plus 3 plus 12 plus 1 plus 16. Right. So the molecular weight of acetaldehyde would be 44. And the molecular weight of water is going to be 18. So now to calculate the mole fraction of acetaldehyde XA, we are going to take moles of acetaldehyde, that is weight upon molecular weight, upon moles of acetaldehyde plus moles of water. Okay, moles of acetaldehyde plus moles of 98 by 18. All right, this is there. So we'll get XA is equal to 0.00828. All right, so this is your shortcut to calculate. Since now you people have understood the concept of conversion from weight fraction to mole fraction, there, or mole fraction to weight fraction, therefore we can directly use this method to convert from weight percent to mole percent. Okay, so that is weight upon molecular weight upon weight upon molecular weight plus weight upon molecular weight. All right, so that is, so we have done the same thing. We have actually done the same thing. We have calculated the number of moles of each component. Then we have divided it by the total number of moles of component A plus moles of component B. So that's what we have done. But this we have done in just one step. Okay, instead of doing so many calculations, we have directly done it in one single step. All right, so we have got 0.00828, and in this case you can see that it is very close to 0. Hence the law that is applicable here is going to be Henry's law. All right, the law applicable here is going to be Henry's law. So by Henry's law, we have PA is equal to HA into XA. We have given PA. The partial pressure of acetaldehyde over the solution is found to be 41.4. So PA is given to be 41.4 and XA is 0.00828. Hence, you need to calculate HA. That is 41.4 upon 0.00828. That is going to be equal to 5000.2 kilopascal. All right, this is the Henry's law constant. All right, this is the Henry's law constant. Now we are going to use this constant in another condition where they have given partial pressure over a 0.1 molal solution. Molal. People remember the unit that we discussed, molality. Anything about this concept? In the first video, we discussed molality. Molality is nothing but number of moles of solute upon mass of solvent in kg. Okay, so this is equal to, the unit is mole per kg, and we discussed that 1 mole per kg is equal to 1 molal. So this means that over here, in this case, we are going to consider basis as 1 kg of solvent. 1 kg of solvent. That means 1000 grams of solvent. Okay, 1000 grams of solvent. This means moles of solute is going to be 0.1. Hence, mole fraction of solute is 0.1 upon molecular weight upon 0.1 upon molecular weight plus again weight. I'm so sorry, just a minute. Here, we are not going to calculate it this way. Mole fraction, right? So we don't need moles of A. We already have it, 0.1. We don't need to divide it by the molecular weight. We have 1000 grams of solvent. So we will get number of moles of solvent as 1000 by 18. Okay. Hence, mole fraction of A is going to be 0.1, that is moles of solute upon 0.1 plus 1000 by 18. All right. So from this, we'll get mole fraction of A is equal to 0.00179. All right. Now, when we have to calculate the partial pressure over the solution at the same temperature, then we need to use Henry's law again. So PA is equal to HA into XA. Henry's law constant we already calculated, 5000.2 kilopascal into 0.00179, which is approximately equal to 9 kilopascal. All right. So that is your partial pressure. All right. So in today's lecture, we have discussed a lot of concepts. We have discussed two very important laws, Raoult's law and Henry's law. And we have dealt with vapor liquid equilibrium. All right. So these concepts are quite important. So make sure you are very clear with all these concepts before we start with our main subjects like chemical process calculations, thermodynamics, and other subjects. Before that, you should be very clear with what is vapor liquid equilibrium, what is partial pressure, what is moles, mole fractions, weight fractions, conversion from mole percent to weight percent. All these concepts you need to be very clear. You should know how to solve these problems, and only then you will be able to easily go with the other subjects. Otherwise, you will start getting confused when we'll go to these important subjects. Therefore, make sure that before you start the further videos, before you refer the further videos, you're clear with this video and the previous videos, because all of them comprise of basics. All right.